The coefficient of determination is something that we can calculate to look at what part of the variation or variability in the response variable is explained by using a straight line model, and then what is still left over that can't be explained. So the correlation coefficient is simply squared, right? So you raise it to the second power, multiply it by itself to create this coefficient of determination, or what we often refer to as the R squared value. Now if you think about R, the correlation, it was between -1 and +1. So when you square it, it is always between 0 and 1 if you keep it as sort of a decimal. Now you can report it as sort of that decimal or fractional number, or you can report it as the percent. But it represents what part of the variability in your Y variable is explained in a straight line model when you use X as the predictor variable. The part left over, everything, right, 1 minus R squared, or 100 minus R squared if it's a percent, is the fraction or percent of variability in the Y variable that is not explained in the model. And we say that that is left to random error, not as a mistake, but just what's not explained by the model. You're always going to want to be able to write interpretations using points 2 and 3, the part explained and the part left unexplained. So for our example, the correlation coefficient was 0.6926, and you can go back to the first output from StatCrunch and look at the R value, the correlation coefficient, and then the R squared value to match these numbers up. But 0.6926, if I round it off to 4 digits, was the correlation for the weights versus tail lengths of wolves data. So if I take that and I square it, I get 0.4797 when I round it to 4 digits. So the 0.4797 is the fraction of variability in the response variable, weights of wolves, which can be explained in a linear model or a straight line model when I use length of the tail of the wolf as the predictor variable. The part that's left over, 1 minus 0.4797 or 0.5203, is the part of the variability in weights of wolves that we say is due to random error. That's the natural fluctuation in weights of wolves that isn't explained by the model. It's that idea that not every wolf with the same tail length is going to weigh the same amount. Part of it is unexplained. So just keep in mind that error doesn't mean mistake in this case. It just means the differences or the variation that cannot be accounted for in the model that you have. Now if we write the coefficient of determination or the R squared value as a percent, we still sort of go through the same process. So we square R, but then we multiply it by 100 to make it a percent. So instead of 0.4797, we have 47.97%. So we would say that 47.97% of the variability in weights of wolves can be explained in a linear model where length of the tail is the predictor, and that leaves 100 minus the 47.97 or 52.03% of the variability in weights of wolves due to random error. You can work with the coefficient of determination as either a fraction or a percent, and hopefully these are pretty easy to convert back and forth. Just don't simply take the fractional number, the R squared number, as a decimal and add a percent sign after it, because then you're not really making the correct statement at that point. But this is just another measure of how well your model works, or what part of the variation in weights the model is accounting for, and the higher the R squared, the better the model is thought to be in general.